Now let's consider these types of limits. The 0 to the 0, infinity to the 0, and 1 to the infinity types of indeterminate forms. These two should be reduced to 0 over 0 or infinity over infinity, so we can use L'Hopital's rule. Here's an example. So we use the same trick as we did for applying logarithmic differentiation. So we let y be this function, x to the square root of x, so we can separate the exponent from the base so that we have a multiplication instead of powers by taking ln of both sides. And then using the rule of logarithm, which gives you square root of x times ln of x. Now we consider the limit of this new function. Once we find the limit of that, then we come here. That would mean we have found limit of ln of y. So then y would have limit e to that answer. So let's start by doing the limit of square root of x times ln of x as x tends to 0 from the right. And this one is 0 times negative infinity type, because square root of x tends to 0 as x tends to 0, and ln of x tends to negative infinity. So this can be written as a ratio, so we get 0 over 0 or infinity over infinity. So let's see if we write it as a ratio, because we can only apply the L'Hopital's rule when we have an indeterminate form 0 over 0 or infinity over infinity. So I'm going to keep ln of x in the numerator, and then square root of x I can write as a power in the denominator. In the numerator is x to the half. So when we move it to the denominator, it becomes x to the negative half. Now, as x tends to 0 from the right, the numerator turns to negative infinity. So again, remember the graph of ln. So that's negative infinity. And then in the denominator, this is 1 over square root of x. As x tends to 0, its denominator tends to 0. So this goes to positive infinity. So we have infinity over infinity type. So we can still use L'Hopital's rule, either 0 over 0 type or infinity over infinity type. So by L'Hopital's rule, this is the limit of, let me write it down here. So this is by L'Hopital's rule equal to the limit of derivative of the numerator over derivative of the denominator, because it's infinity over infinity type. So you get 1 over x for derivative of ln of x. Derivative of x to the minus 1/2 is minus 1/2 x to the minus 3/2. Before we decide what kind of limit this is, let's do some algebra to simplify this. If you multiply both numerator and denominator by x to the 3/2, what do we get? X to the 3/2 divided by x is x to the 1/2. X to the 3/2 times x to the minus 3/2 would be just 1, and there is a minus half in front, and this is what we get. Now as x goes to 0, the square root of x goes to 0, so 0 divided by negative 1/2 is 0. But this is the limit of that. This is the limit for the square root of x times ln of x. That means ln of y tends to 0. So let's write that down. So this means, ln of y tends to 0. So this implies y tends to e to the 0, which is 1. And ln of y is ln of x squared of x, so the y has to be x squared of x, x raised to the x squared of x. So this tells us that y tends to 1. So the limit of x raised to the square root of x, which is the y here, as x tends to 0 from the right, is equal to 1. Now let's look at another example of these types, 0 to the 0, or infinity to the 0, or 1 to the infinity. So again, because exponents are involved here, this trick works. Take ln, let the expression be y, then take ln of that, and then rewrite this algebraically as a ratio, so we get infinity over infinity or 0 over 0 type. So we can apply LHopital's rule. So here's another example. X to the 1 over x as x tends to infinity. So here the base x, this tends to infinity because x tends to infinity, and the exponent tends to 0 because denominator gets bigger and bigger and bigger, so 1 over that tends to 0. So this is the type infinity to the 0 type limit. So the other problem we just did was 0 to the 0 type. So here this x tends to 0 and the square root of x tends to 0. So this was 0 to the 0 type. And now the second example is infinity to 0 type. That's this. And for this, again, we use the trick by setting this equal to y and then taking ln of both sides. So ln of y is 1 over x ln of x, or just ln of x over x. Okay, so now we consider this new limit ln of x over x as x tends to infinity. Now ln of x goes to infinity as x goes to infinity, x goes to infinity as x goes to infinity. So L'Hopital's rule applies because it's infinity over infinity. So we have the limit as x tends to infinity of a derivative of ln of x, which is 1 over x over derivative of x, which is 1. And that is equal to 0. Because as x goes to infinity, 1 over x goes to 0. And we have 0 divided by 1. So that means that ln of y tends to 0 because ln of y is ln of x over x, and that's the limit we just found. So we can write ln of y tends to 0, so that implies y tends to e to the 0, which is 1. So the limit of x to 1 over x as x goes to infinity is 1. So this is as x goes to infinity, and we just found that to equal 1. Now let's try this last example. Here x goes to infinity, so that makes 1 over x to go to 0, so the base goes to 1. And the exponent, which is x, that goes to infinity. So this is 1 to infinity type, which is also indeterminate. So therefore, to separate the exponent from the base, we let this be called y, and then take ln of both sides. So ln of y equals, by using a rule of logarithms, ln of the right side is x times ln of 1 plus x. Now our new limit is the limit as x tends to infinity of x times ln of 1 plus 1 over x. So let's see, x goes to infinity. This 1 over x goes to 0, right? 1 plus 0 is 1. So this tends to 1. And ln of 1 tends to 0. So we have, this is infinity times 0 type. So we need to turn it into a 0 over 0 or infinity over infinity. So let me keep the log in the numerator. So this limit equals the limit as x tends to infinity of ln of 1 plus 1 over x divided by 1 over x, because this x, when you move it to the denominator, it becomes 1 over x. Now let's try again. The numerator, just like above, the ln tends to 0. And 1 over x tends to 0. So this is 0 over 0 type. And L'Hopital's rule applies now. So we take the derivatives and form a new ratio. Derivative of ln is 1 over 1 plus 1 over x. And then by chain rule, we multiply by derivative of 1 plus 1 over x. Derivative of 1 is 0. Derivative of 1 over x is minus 1 over x squared. in the denominator, we just have 1 over x, and its derivative is minus 1 over x squared. Now, when you simplify that expression, this becomes the limit. In any of the limit problems, before you decide what to do next, try to simplify the expression as much as possible. So you see, the numerator has a numerator of minus 1 over x squared. That can cancel this. And then as a result, we have 1 over 1 plus 1 over x. And now we can let x go to infinity. So 1 over x tends to 0. So you have 1 over 1, which is 1. Now, this was the limit of x times ln of 1 plus x, 1 plus 1 over x, which is ln of y. So we have found derivative, the limit of ln of y. Okay, so because this limit we just did was ln of y. ln of y tends to 1. So that means the y tends to e to the 1, which is e. So we found that the limit of 1 plus 1 over x raised to the x as x tends to infinity, which is in the form 1 to infinity. If you go back up here again, so this was a type 1 to infinity indeterminate form, and in this case the limit happened to be e. By the way, this is one of the ways we can define e. So the definition of e is the limit of this expression as x tends to infinity. There are different ways to define e. This is just one of them. So here's the last video on LHopital's rule. There are some examples to try from the book.